Hello, my name is Apio Diane. I'm going to be talking about an introduction to machine learning with my colleague, Maria Karungi. Um, Beginning with machine learning, a characteristic of machine learning is the concept of self-learning. It is an application of AI that can provide the system with the ability to learn all on its own without the help of a programmer telling the system what to do. The system is able to improve its performance based on data and other information without directly programming commands. Though it's important to note that the human programmer is still responsible for like feeding the data into um feeding the data into the model, selecting an appropriate algorithm, adjusting the hyperparameters, which is like the settings, and to like reduce the prediction error. And yes, types of machine learning, you have supervised learning and unsupervised learning. So supervised learning involves like training the models on labeled datasets. Um, the basic definition of a model is a mathematical representation of a system. So in supervised learning, it involves like the ability to extract patterns from known examples and use those insights extracted to develop an outcome, a repeatable outcome. I read somewhere that the company Toyota designed its first prototype basing like on the same concept of supervised learning, whereby they did not develop like a new manufacturing process for cars. They, however, got another car, which was a Chevrolet car, another company, and they took it down and then they observed these individual components of this car. And from there, these Toyota engineers unlocked sort of like the design process that the Chevrolet car had been designed with. Yes, and then in supervised learning, you have two algorithms. There is regression and classification. In regression, you have a data set with input features, for example, number of rooms corresponding to like output values, for example, like house prices. So, like therefore, like this regression algorithm learns the relationship between these input features and the output values. Hence, a trained model is able to predict the output value for like new instances or like unseen inputs. Then in the classification algorithm, you have a dataset with input features, for example, images, text, numbers, etc. And then you also have labels, for example, is it a dog or not? Is it one or zero? And this algorithm learns patterns and relationships between these features and labels. Therefore, a trained model is able to predict the labels for new instances. Then you move on to unsupervised learning, where there's basically no prior knowledge. The algorithm learns patterns and relationships in data without any labeled examples. And the algorithm here is clustering and anomaly detection. Clustering is just like grouping similar data points together based on like their features. And then like anomaly detection is just like detecting or identifying like unusual or just basic abnormal observations in data that do not like conform to the expected pattern of that data. And of course, additionally, there are other types of machine learning, semi-supervised, reinforced, and self-supervised. Yeah. Then moving on to the concept of end-to-end machine learning, which is a field of AI, which is basically focuses on entirely building and deploying and maintaining a machine learning model. It focuses on the end-to-end machine learning pipeline, which covers all the steps that are involved in building, deploying, and maintenance of these machine learning modules. Basically the steps: data collection, which is gathering data from various sources. You move on to data cleaning and processing, which is removing like inaccuracies in data. Just to simply put it like that. Then feature engineering, which is creating new features, modifying or selecting new features from raw data. You have model selection, model training, model evaluation, hyperparameter tuning, which is like adjusting the settings of the model like to improve performance, and then deployment and maintenance. Then let's move on to exploratory data analysis and feature scaling. EDA is the process of visually and statistically exploring data and understanding its underlying structures, patterns, and relationships. And the insights got after that analysis process of understanding the structures are then extracted and created and like curated to prepare for data modeling. Techniques here involve like visualizations like histograms or scatter plots, or statistics like summary statistics like mean, standard deviation, things like that. Then feature scaling is transforming numerical features of a dataset to a similar scale. So basically a common scale. It is necessary in machine learning algorithms that are sensitive to the scale of features. Like, for example, if one has a larger range, it dominates the model, leading to like biased results, poor performance, and the common types is standardization, normalization. So there's an example that I've put there of that I've put in the slide just to simply show how feature scaling is. This is an example of normalization, or sometimes you can call it min-max scaling. And this is the formula, which is x minus min x divided by max x minus min x. So you have x is the current x. Let's say if you're at 20, age of 20, that will be your x. If you're scaling the edges and you're at 20, that will be your x. If you're at 30, that will be your x. If you're at 40, that will be your x. And then, so that's how you can basically scale data that you have been given. And in this case, we're given age in years and income in dollars. That was just a basic example. But whereas in standardization, you just subtract the mean of the data and then divide it by the standard deviation. Now moving on to linear regression. It's a linear model that predicts continuous output variable based on one or more input features, and basic formula is y equals to beta 0 plus beta 1 times x plus epsilon, where y is the continuous output variable, x is the input feature, beta 0 is the intercept, beta 1 is the slope coefficient, and epsilon is the error term, which represents the random variation in the data. A basic example, so suppose we predict the price of a house based on its size, and then we have that data set given. So the linear regression equation here will be house price is equals to beta 0 plus beta 1 times house size, and where beta 0 is the price of the house with 0 square feet, and then beta 1 is the change in price for 1 square foot increase in size. And using a dataset, we train the linear regression model to find values for beta 0 and beta 1. And then once this happens, we can make the prediction. For example, if we want to predict the house price with 1,600 square feet, the model would predict it using the equation house price is equals to beta 0 plus beta 1 times 1,600. And let's say the trained model outputs that this house price is equals to 250,000. This means that according to the model, the house with 1,600 square feet is likely to cost about $250,000. This is a simple example that just illustrates the basic concept. And the case, now moving on to logical regression, for it's used for binary classification, and it models the probability of a binary outcome based on predictor values, and that is this equation as seen on the screen, where P is the probability of the positive class, E is a natural log, Z is the weighted sum of input features, and it's calculated from beta 0 plus beta 1 times x1 plus beta 2 times x2, and so on and so forth, where beta 0 is the intercept, beta 1 and beta 2 and so forth so on are the coefficients of the input features, and x1, x2 up to xn are input features. And then we look at KNN, which is K-nearest neighbors algorithm, which is used for both classification and regression, and operates on the principle of feature similarity to predict outcomes based on closest training in the feature space. And mainly, I think here is the steps involved in KNN, and they're as seen on the screen. A few challenges arise here: visualization and dimensionality challenges. And visualization challenges arise when dealing with high dimensional data, such as the data we deal with in KNN, because it's difficult to visualize data with more than 3 or 4 features. And this can make it hard to understand the relationships between the features and identifying patterns in the data. So we can use like scatter plots to visualize the data and their classifications to help overcome this challenge. Whereas in dimensionality challenges, they are heavily prevalent in algorithms that rely on distance calculations. Kenya's neighbors performance can degrade with high dimensional data due to the curse of dimensionality, which is a phenomenon that occurs when the feature space becomes sparse, making it difficult for the algorithm to find meaningful patterns. So therefore, to overcome this, feature scaling is essential. And dimensionality reduction techniques such as PCA, which is principal component analysis, can also help. Lastly, we are going to explore the concepts of decision trees, entropy, and information gain. And entropy is a measure of impurity or disorder in a data set, quantifying the uncertainty in predicting the class of a data point. And that is a formula for entropy, whereby H in brackets X is entropy, P in brackets X is the probability mass function of X, and then the sum is taken all over possible values of X. Of course, log 2 is the logarithm of base 2, so base 2. Information gain measures the reduction in entropy after a dataset is split on an attribute, indicating how effective an attribute is in classifying the data. Again, its formula is right there, where information gain of feature X with respect to target Y is equals to the entropy of target Y minus the conditional entropy of target Y given feature X. And then we look at decision trees, and these decision trees are like models for classification and regression and splitting data into subsets based on feature values. The implement moving on to decision trees, they are a type of supervised learning algorithm, and they use for classification and regression, splitting data into subsets based on feature values. And to enhance the performance of decision trees, we look at pruning, which involves removing branches from the tree to reduce complexity and prevent outfitting. There are two types: pre-pruning, post-pruning. Pre-pruning stops the tree growth early based on certain criteria, and post-pruning removes branches after a tree is fully grown based on validation data. And lastly, gain ratio is a modification of information gain that accounts for a number of branches created by splitting on an attribute, hence helping to avoid bias towards attributes with many values. And the formula for gain ratio is gain ratio of feature X with respect to target Y is equals to information gain of feature X with respect to target Y divided by the intrinsic value of feature X, also known as the entropy of feature X. Thank you.
Good evening, sir. My name is Karungi Maria Daphne from Year 2 Computer Science, and I'll take you through the last 3 modules of the diploma course, which is module 5, 6, and 7. So module 5 is about ensemble learning, which involves combining many mediocre models into one super model. It has 2 techniques mostly. There is bagging and there is boosting. Now for bagging, it's the same as aggregate bootstrapping, which is the idea of creating different models using different bootstrapped training sets and average their prediction to produce the final output of the model. For example, you have a set that contains values 1, 2, 3, and 4. Those are 4 values. So you generate different sets with the same amount of values as the original set. They can be 10 or even 20, but with the same amount of elements as the original set. And these elements, these sets contain random elements, and there's replacement. So you can replace the elements there. For example, set 1 can have 1, 2, 2, 4. Set 2 can have 1, 1, 3, 4. So you can repeat some elements also. Then why bagging? To reduce variance and overfitting and to reduce the chance of outliers. So the steps in bagging are mainly 3. Step 1, generate these different bootstrapped sets, then train these machine learning models on these sets, and finally get the prediction average of the output. So as I said earlier on, you get different sets from the original set that you want to sample. Then you train these sets based on the model you want to use on them. Then finally you get their prediction average, or mean, for the final prediction. Then the out of bag error. For example, that's okay, out of bag basically means that you have a set of 1, 2, 3, and 4, and you pick out, let me say you pick out 1, 2, 2, 3. So out of bag will be 4 because they've left out 4. So that's what out of bag means. The ones that you've left out from the ones from what you've picked out. So mean prediction error on each training sample X using a model that did not have X in their training set, as I explained before, out of bag error. So boosting, which is sequential tree growing with weighted samples. So bagging is kind of parallel, then boosting is sequential. So boosting has adder boosts, that's adaptive boosting, which uses decision stamps as weak learners, assigns weights to samples based on errors, then combines learners using weighted majority voting. How boosting works is that you train a weak learner, then you identify errors, you weight the errors, train the next model, then combine the models, repeat until errors are minimized. So random forests. About them, they are modified backing algorithms as well as collection of decorrelated decision trees. For every tree, we subsample the examples with placement bootstrapping. Then for each sample, we choose the attributes at random. Then we build the tree only on these random features. Then you classify the tree by taking a majority vote on the classification yielded. Then the pros and cons. The pros are robust to outliers, works well with nonlinear data, that's lower risk of overfitting, and runs efficiently on a large set of data. Then the cons are slow training, not suitable for linear methods, best while dealing with categorical data, and greedy algorithm doesn't yield the optimum tree structure. So the pros are same number as the cons. They want support vector machine, SVM. So SVM is a supervised learning algorithm used for classification and regression. It divides data into classes by finding the optimal hyperplane with the widest margin between classes. The key concepts in SVM is the hyperplane, the margin, and the support vectors. Now, let's say you have two scoops of ice cream, strawberry and vanilla, and you want to separate them from each other, the different flavors. So that space between those two scoops of ice cream, that's what we call a hyperplane. So hyperplane is a decision boundary separating classes. In the margin, the distance between the hyperplane and the closest data points, e.g. hard and soft margins. In support vectors, data point closest to the hyperplane. Then linear SVM works when data is linearly separable. For example, let's say you have a graph, and that graph has different points that you've plotted. Now, if you can easily draw a line between those two to separate, let me say, data points A from the data points B easily, without any hardship. So that's a linear SVM. So it's easily separable linearly. Linear is means a line, so you can easily draw a line between those different points. Then nonlinear SVM uses scalar functions, for example, Gaussian radial basis function, polynomial, sigmoid, cosine similarity kernel to map input data into higher dimensions for separation, and is used when data is not linearly separable. So for nonlinear, as it's explained itself, nonlinear, you can't really draw a line between the data points, so they're not really separable easily. So we use kernel functions that map input data into higher dimensions for separation. Then more about SVM. We have key parameters in SVM. We have the C and we have the gamma. Then the standardized in the pre-processing technique that transforms features to have a mean of 0 and a standard deviation of 1. Applications can be used in SVM, in PCA, in K-means, and it also ensures that all features contribute equally to the model and prevents certain features from dominating due to their scale. Then next to module 6, that's principal component analysis, that's PCA. It's unsupervised dimensionality reduction technique used to simplify large sets of data while preserving the most important information, the variance. So the key idea here is to basically project data into a lower dimensional space by finding new axes that capture the maximum variance. And the goal of this is to reduce the dimensionality of the data while keeping the information loss to a minimum. How PCA works is that there are 4 steps. The first step is standardize the data set, then you compute the covariance matrix, Then you find the gene values and the gene vectors of the covariance matrix. Then you project the data onto the top K gene vectors. And more about PCA can be applied in image compression, data visualization, facial recognition using gene faces, then in pre-processing step for classification tasks. Then the add advantages, because we have them here, which is making computation faster, removes uncorrelated features, helps visualize high-dimensional data. Then it can lose interpretability, then sensitive to scaling. Those are the advantages of PCA. Thank you very much.